Today we're going to be looking at Nastran results when you're working with spherical coordinate systems. So here's an example where we are looking at some stresses in the spherical coordinate system. We'll do this for stresses and displacements. And quick comments before starting. Today we'll be using the Postprocessor web app to look at the results. The Postprocessor web app is free to MSC Nastran users. Also, the Postprocessor web app is only compatible with MSC Nastran. It is not compatible with any other Nastran version out there. If you want to start using the Postprocessor web app today, you can visit theengineeringlab.com. And here in the top right, there's a button. You click on free download. You can start the process of maybe downloading your own installer for the Postprocessor web app. Now, this example is actually, let's see, what example is this? I believe this is example 5 from the Patran post-processing manual. So this manual goes into more detail regarding the materials, the loading, the boundary conditions. So if you want to learn about that, I refer you to this document. What we want to look at are the stresses for this model that is using spherical coordinate systems. So to start off, go to the home page of the web app and click on tutorials in the user's guide. Go to the post-processor tutorials, navigate until you get to this section, CQUAD4 stresses and deformations in spherical coordinates. Click on this link. You get a zip file. This zip file is going to contain the bulk data file that contains this Nastran model, and it contains the H5 file. And the H5 file contains the results of the Nastran analysis. So now let's go ahead and go back to the home page. Let's click on the viewer, and let's upload the bulk data file. And we are going to upload the H5 file also. Let's go ahead and do that here. So we've defined, or we've uploaded these files, and I immediately opened the post-processing web app. But before that, let's talk about the displacement coordinate system. So let me go ahead and turn off the elements. And right now what we get shown are the element edges for this model. If you click on FEM label, click on this option called Display Coordinate Systems and display the displacement coordinate systems, or the degrees of freedom. So if you look here, the degrees of freedom are not parallel to the basic coordinate system. So here, normally when you're using Nastran, your degrees of freedom are parallel to this bottom coordinate system. So this is the basic coordinate system. Your degrees of freedom are normally parallel to this x-axis, the y-axis, and the z-axis. But here, since we're dealing with the spherical coordinate system, and here in the top right, this is our spherical coordinate system, you can see that the degrees of freedom are different. The x-axis, if you will, this is actually pointing away from the origin of the spherical coordinate system. So I wanted to point this out, that with the Postprocessor web app, you can display your displacement coordinate systems, which are also known as the degrees of freedom. And let me open that file actually. And let's go ahead and talk about the displacement coordinate system here. So if we scroll to the very bottom, this is the entry for the spherical coordinate system. So you can think that, let me zoom out here. That entry has defined this spherical coordinate system that we have here. So let's zoom in very closely. So this is the spherical coordinate system defined by this one entry. Now, if we scroll up a little, we get the grid entries. This field, let's go ahead and count out what field that is. So this is field 1, field 2, field 3, and then we have fields 4, 5, and 6. So this would be field 6. And then here in this last field, this is field 7. Right. So this is field 7. So this specifies the coordinate system used to define the degrees of freedom. Normally, it's blank. Normally, the degrees of freedom are parallel to this bottom coordinate system, if you will. Alternatively, if you use 0, that's also the basic coordinate system. But here we said, no, we want to use a different coordinate system. Our degrees of freedom are now defined using a spherical coordinate system. And here we're looking at that right now with the fem label tool. So let's go ahead and maybe display the degrees of freedom again. So you can see that the x-axis, if you will, it's different for every node or grid. The y-axis, the z-axis for each node, it's different depending on where you are in space. So now, with this, let me look at one last thing. Let's go and look at the P shell entry. Okay, so it seems the P shell entry. That's okay. We won't worry about that today. Let's open the post-processor web app. Let's now start thinking about the results. So maybe we'll go ahead and turn on the element edges. So let's go ahead and open the model display panel and turn on those edges or faces. And now we're looking at the magnitude of the deflections. Let's go ahead and take a look at the radial values. Here, we're observing the displacements from the basic coordinate system. So you can think of this bottom left-hand axis being the basic coordinate system, but we want to view the displacements or deflections in the spherical coordinate system. So we'll go ahead and select 1 here for the spherical coordinate system. So now we're looking at the values along the x-axis of the displacement coordinate system. We're looking at the y values, the z values, and so on and so on. That's how you do that. And then here for the shape, we'll do the same. So we'll select the X component, and let me see if I can show you what the deformation looks like. Okay, so here let's go ahead and up the scale factor to maybe 100. And then if we turn the shape plot on and off, here you get an idea of what the X direction of the deflections is. So it's moving or expanding radially if you think about it. So that's how you look at the deflections at least. Let's go ahead and look at the stresses. So let's go ahead and select stress and select this subcase. Let's look at maybe the sigma x stresses for the bottom of the thickness. And let's look at maybe the corners. And let's turn off the shape plot. So let's click this green button to turn it off. Here in display directions, this is only visible when you turned off the shape plot. And we'll mark this as yes. And now you get a general idea of the direction of your stress tensor. So the red axis is the sigma x direction of the stress tensor. The y axis is the direction of the, the sigma y stress. So right now we're looking at sigma x for the bottom, sigma y for the bottom also. If we wanted to, we can also display the von Mises stress. You can do this for the corner or the center. And there's a diagram here. Let me show it real quick. I think this diagram will help you better understand what's going on here. So when you look at the output for stresses or strains for maybe a quadrilateral element, you get 2 options for stress output. You can either output the stress tensor data at the center of the element like you do here, or you can output it for each of the corners of the elements as you see here on the left. Also, these elements have a thickness to them. So you get data for the bottom of the thickness and you get data for the top of the thickness. So right now, a moment ago, I was displaying the sigma x stress. I think it might be worth showing you that again. So here in the field, I can display the x1, which is the normal, and the x stress component. This is the sigma x, and I'm doing this for the bottom. I can also switch to the top. So now I'm looking at the normal x stress at z2, which is the top. So I can only display one component at a time for either the top or the bottom. So right now, I'm displaying the sigma x stress for the top. You might be asking, okay, what does sigma y look like for the bottom of the thickness? So let's go ahead and do that right now. Sigma y for the bottom. Here we want to use the corner option, and we want to switch to y1, which is the bottom. So right now we're looking at sigma y for the bottom, for the corners of the stress tensors. Here you have an option if you want to look at the maximum and minimum values, you can do that here. And here we're getting a stress of about 20,000, which I believe aligns with the expected stress in the Patran manual. So here you can see the sigma 1, the sigma 2, those stresses happen to be at 20,000. Okay then, anything else to go over with? Nope, I think that's pretty much it for this tutorial. Just as a reminder, the Postprocessor web app is free to any MSC Nastran user. If you want access today, you can go to theengineeringlab.com. You can click on free download, and there you'll find a sign up form for the Postprocessor web app. Also, the Postprocessor web app is only compatible with MSC Nastran. And with that, I think I'll stop here. And as always, thank you so much for watching.